Hello everyone. In this video we are going to talk about particle filters, or you might call them sequential Monte Carlo methods, which are used a lot in state estimation of systems for which the Gaussian assumption for initial states, for noise, and in general the posterior distribution of the states is violated and it cannot be used, like robot localization and so on. In those cases, we use this simulation method of particle filters, or Monte Carlo, and they are very useful, although they are being basically approximate methods. So before I start, text equations and some of the pictures are taken from Wikipedia. Object Tracking Particle Filters Made with Ease by J. Darko, and the amazing book of Probabilistic Robotics by S. Throne. This is one of the best books out there. So let's start, see how we are doing it. So as I said, this is used when the Gaussian assumption is violated. We cannot really assume such a thing. And so we cannot, for nonlinear systems in general, we cannot use extended Kalman filter. So we use this method, as opposed to extended Kalman filter, where the probabilities, the average, the sigma matrix, right, the covariance, are propagated, you can see here, through analytic formulas. Here, the propagation is done through simulations. Okay, so as I said, they are approximates, and the good thing about them is they are non-parametric. So we don't need any parameter, right, p or sigma mu or anything like that. So they still have prediction and update stages, and their overall behavior is to use the knowledge in prediction step and to use the measurement in update step, but based on some simulations. So the method uses a bunch of samples, which we also call particles, and you might show them by x sub t at I, right? So I is the ith particle and t is that time. These particles represent the posterior distribution of your states. So if we want to define a particle, we can say each particle is an instantiation or representation of the state of the system at time t. If we denote the set of all these particles by this capital X times t, right? And here we have m particles in the system, right? At time t we have m particles, where m typically has to be a large number. If you want to approximate the distribution by some particles, we have to use a large number of particles or samples. You might say, why is it that in your unscented Kalman filter video you only used a few points called sigma points? The reason was, in unscented Kalman filter we were not going to estimate the entire distribution. We were just going to estimate the transformed average and the transformed covariance matrix. So we wanted to estimate two parameters after transformation. Here we are going to estimate the entire distribution by a bunch of samples. So we need a large number of samples, typically more than 100. And as this m approaches infinity, your approximation becomes close to basically perfect accuracy, but you cannot do that. So in many simulations, we use a large number of particles, more than 100, and most of the time actually more than 1,000 particles are used to do a good job. Okay, and one of the things they can do in some adaptive version of particle filters, they make this m to be a function of time. Okay, as you go on, you'll see that you get closer and closer to your actual state, and so you don't need as many particles as initially. So you might need to reduce the number of particles to save some computation. So what does particle have? Each particle has two components. One is, of course, the state of the system at time t. that mth particle, right, has a approximation of a state of the system, plus it has something called the weight of it, or the importance factor, which is shown by Wt sub m. Okay, and what is this W? That's the probability of that particle being sampled from that particle distribution. So the particles that have higher probability of coming from that distribution you want to approximate, they get bigger weights. The ones that are less likely, they get smaller weights. Okay, so there is the algorithm here, and there are some pictures that I'm gonna explain. But before I go through all of this, I want to show you in an example for robot localization, right? I want you to see in practice what is it that the particle filter is doing, and then we go through the math and these good pictures. So here, let's say that we want to locate a robot in this room here. Okay, so we have this room, or 3 rooms you might call it, in this environment, and let's say the robot here is this pentagon, and this, what you see here, is what you might call the occupancy map, or occupancy grid map, right? So here, if some area is black, in this case, that means you cannot go there. If it's white, then you might be able to navigate. So initially, I have no idea where my robot is, so anywhere with the uniform distribution, I can have a particle. So each one of these blue circles can represent where my robot can be at the moment. Okay, I have no idea. Then I have some sensor on my robot. It could be a camera or a range sensor. In this case, let's say it's a range sensor, a LiDAR. And this LiDAR observes, right? You know, if you have a robot anywhere, this LiDAR here is going to send the rays in some range and get some measurements, right? So here maybe detects that. So right now, let's say the measurement that my robot detects, the LiDAR, is like this. Well, what would you do? You say, now I look and see which one of these particles, if I put the robot centered at each and every one of these particles, which one of them will see something similar to this shape? Because this sounds like there is a corner on the left side, there is a straight wall on the right side, and there is an opening in front of the robot. And if you look at all different possible positions for all of these particles, if you center the robot at all of those particles, you see that in these 3 positions, you can have such observation, you can have such measurement. Okay, it's only in these 3 positions that you see the corner, the wall, and the opening at the same time. And the corner is on your left side. You might say, what about here? Well, if your robot is facing this way, then if you look, actually this corner is on the right of the robot. So it is like this, and if you transform it 180 and bring it here, it's gonna be like that. Okay, if you rotate it 180 degrees. Okay, and these 2 are different, right? Here the corner is on the right, here is on the left. So that one is not included. Okay, so there are 3 positions that are available. Now what do I do? In the past, I equally assumed that the robot could be in all of this. Now I know that, guess what? For the particles which represent the robot position in these 3 positions, I give them bigger weight, so I make those particles bigger. I give them a bigger weight, so I draw them bigger here. And the rest of the positions that are less likely to be the robot position, I reduce their weight, so you see I made them smaller. This is what? This is updating the weights based on the likelihood of this measurement given the position of the robot. Yeah, good. Then what? Then I look at the commands of the robot, see how the robot is going to move. So if it's a differential drive robot, I look at the commands of the left and the right motors and see, let's say the command that I read is move both of the tires in the same direction with the same RPM, which basically means go straight, move forward. If these three positions to move forward, what's going to happen? So this guy is going to pass through that opening, this guy is going to pass through the opening, this guy is going to pass through the opening. So this robot comes here, this one comes here, this one comes there. Let's say it's enough to pass through the opening. Okay, so now what do I do? This is the prediction. Here I'm predicting that with these commands of the robot. These are the new states of the system. Okay, so with that, I move the particles the same amount that the robot is supposed to move. So I bring the particles here. Then what? You might say, what happened to these small ones? Here is the trick. Now I go ahead and the small particles that were very small and very unlikely to represent the state, I get rid of them. I threw them away, I discard them. Instead, what do I do? In the positions that are likely, I'm going to resample. So you see here, I only had 4 big particles. Now, if you look, I replace those 4 big particles with 8 smaller ones as big as these original ones. So I resample basically here. I say now with all of these positions, I give them again the same likelihood, smaller likelihood, and then I transform them, I move them here. So now, instead of having particles all over the place, I only have particles in these 3 positions, but all with equal weight, smaller weight, and then I make another measurement. I read the measurement of the robot again, and let's say this time the measurement is like that, a corner on the left only. So now I look and say, hey, if this guy is to read the LiDAR, well, this guy is probably going to see a left corner. Well, that makes sense. Here, if this guy is to read, if you look at the race for this guy is going to read what? A corner, corner, but maybe a couple of corners, and it's going to be on the right side. And if this one is to read anything, that is going to be more complicated. It's probably, even if it cannot read this gap, it is going to read something like this. So although it has a corner on the left, but it has this extra feature, and there is probably, it can read this gap too. So now out of these 3 positions, only this one is matching that measurement. So what do? I bump up the weight for that position and reduce the weight for the other ones. And if I want, I can repeat that. But right now, if I resample again, I get rid of all of these small ones. And here I would what? I would again give equal smaller weight to only this area. But now you see, after a few iterations, from I don't know where I am, equally likely everywhere, now I'm only concentrated here. And if I look at their centroid, maybe here is where I think my robot is. And if I fit like a small Gaussian or something, or if I get their sigma, now I can have some probability as well, some distribution, or you might call some variance. Okay, and as you do more and more measurements, probably some of these 8 particles or 10 or whatever will also be discarded. So you might move more toward the center of them, or toward the left of them or right of them. So over time, the number of particles will go down, and you get more and more certain in where the robot is. Okay, so you see, it's very simple and effective idea, as long as what? As long as you have enough of particles. Because in real life, These measurements are not as perfect as this. And so you have to fit this unperfect measurement to relatively these perfect maps that you have ahead of time. Okay, and by the way, in here, we assume that we know the map of the environment. In the future video, I talk about SLAM. In SLAM, you don't even know this map, and you have to make that map at the same time, which makes it very hard. That's why SLAM is a complicated topic. Okay, so, but right now we assume that we know the map. So first thing is, we have to basically match these unperfect measurements to these perfect maps. So your measurement is not going to be as good as this. Your measurement probably going to be something like this. Or, you know, let me not put that. Maybe some gaps here. And with some maybe distorted walls. So something like that, and you might even get one of these above the other ones or something. So you might get something like this as opposed to that. And so your probabilities are not going to be 100%. Say, hey, 100% I'm sure it's this one, not any of those. You have to do some probability. So you give some probability to this one and some probability to those ones that they see this measurement, and those probabilities are basically those weights that you are going to what? You're going to give them. Okay? So now that we have seen the example and we know what it is, let's look at a little bit more formalization and formulation of it with some more pictures. And the algorithm here, the basic particle filter, because that's the basic one, that's like the vanilla one. There are so many versions of this which try to address the shortcomings. But what it says is you have three things. One is the set of particles, one are the commands of the robot, and the observation ZT. So it says start your particle set with 0, so assume that you don't have any particle. Now for M1 to M, which is the number of particles, do. What do you do? Go ahead and sample your x of t based on the probability of x of t given u of t and x of t minus 1. So what is this? This is your transition probability. Okay, so this is the chance of your state given the previous state and what? And the command. This is what we call the state transition model, which we had in the past several times. And basically, this is your prediction step. So u is the input to the system, and you see that your x only depends on x minus 1. So your system follows a what? You're right. It follows a Markov assumption. Okay, only previous state has effect on the next state. Nothing before that. Okay, yeah. And you do the prediction step, and then it says once you move the particles based on the prediction, as we said, now look at what? Now look at the measurement that you are making, compare it against what you have, and update the weights. So you see here that based on the probability that such measurement is made at such state, update the what? Update the weight. So this function here, P of Z, P of observation given the state, is what we call the likelihood function, right? So this is what your likelihood of observing given the state. And once your state and weights are updated, go ahead and add them to your particle set. Okay? So this is the part that you do the prediction and weight update. And then, remember we had something else that we discussed, and that was resampling. So once you get your updates on the weight and state, now you have to resample. Okay, why do you need to resample? Let's talk about that. If we don't resample and we keep increasing the weights, or here the size of these particles that are more likely, and smaller to the particles that are less likely, very, very fast, some of the particles will dominate the rest of the particles. And so now your posterior probability distribution, which could be in this case multimodal, is going to be only approximated by maybe 10 or 12 or 15 particles or so. And that is not a good approximation. So here, let's say your probability distribution is something like this, or maybe one of them is a little bit smaller, so you have something like this. But if I want to approximate this, I cannot just have these particles. That is not enough, because from these, guess what? I can approximate some other things. I can say, hey, this is, for instance, is this guy. Yeah, or something else. So if I want to approximate this at each step, I still need to have a sufficient number of what? Particles. Once I have a good number of particles, right, then I cannot go with this blue curve, right, because this blue curve does not represent all these particles, right, and that will help me basically still be able to, before being so sure about the final outcome, I still can what? Represent my posterior probabilities with sufficient accuracy and avoid a problem which is called degeneracy. Okay? So what you need to do in each step is to resample the weights or the importance factor, as I said. And if a particle has negligible weight, you replace it with new particles, but where? Not in the same location, in the proximity of the particles with higher weights, right? So here, these guys I'm going to get rid of, but instead of now these 4 big particles, I have 8 or 10 or 12 or more particles, right? So I'm resampling in the vicinity of what? These ones with bigger weight. So I'm not going to stick to these 4 big weights. I'm going to do what? A lot more smaller weights, but in the same region. Okay, and that helps you over time keep track of these distributions, because if you do this as fast as I did here with 2 measurements, there is a good chance that because of the noise in your measurements and because of the inaccuracies in your prediction model, you go wrong, okay, when the model is complicated. So when this map is not as simple as this. So you want to get to where you are in this case, but not super fast in a couple of iterations, because there is a chance that your measurements, and as I said, are biased, and you get a wrong conclusion. So this resampling is an important thing, and mathematically you see that for m equal 1 to m, what does it do? It draws the sample again, but with probability equal to their weights, and then add these new samples to the sample set. So it re-evaluates and redraws samples from what? From the distribution based on their weights. Okay? So we talked about the update model and the prediction, the transition model or the prediction. We talked about how the weights are measured based on the likelihood. Now, if you have the weight from a previous step, one of the things you can do is, here is when you start, but if you want to keep updating the weight, you might multiply this likelihood by the previous weight and get the new weight. Okay, so this is good for instantiating the weight when you start them, but when you want to keep updating them, you want to multiply your likelihood by what? By your prior information. This is the prior information, this is the likelihood, and that gives you an approximation of the posterior for the weight. Okay, yeah? And here, these are some good pictures from this paper, Object Tracking Particle Filter with Ease by Draco. The algorithm is coming from probabilistic robotics, but here, these pictures also show some good things, right? So you see here are the weighted samples from the previous step. Some of them have bigger weights, some of them smaller. Now you resample. Resample means what? Means I don't care how big they were. The only thing I care about the big ones is I give them more samples. And if the areas were small weights, I'm not going to give them samples. Okay? But still, I redistribute the weights equally instead of some bigger and some smaller. And then these particles with equal weights in the more likely areas, I apply my transition to them, right? Which is called the motion model or drift or the prediction. So from time t minus 1 to time t, now let's say they are all moving like this. So some of them going to the left, some of them going to the right. If you have a chance to apply noise to the particles, go ahead and apply noise to that motion. So here, this transition, if you can, go ahead and add what? Some noise to it, if you can. If you know something about that noise, you can apply that noise. If you don't, then you can skip this step of diffuse. And then again, with these, go ahead and do the measurements. And those measurements with bigger likelihood, those states with bigger likelihood of making the measurements that you have, you give them bigger weights. Those that are less likely to make such measurements, give them smaller weights. Okay, and keep repeating that. So it's just a bunch of operations done in loop. Okay, so I guess I talked about everything I needed to talk. Update the state, degeneracy, resampling. So they're amazing. They have some limitations too, so let's talk about their limitations and some properties. One of the things they have is they are highly computationally demanding, and you can guess, right? When you are dealing with thousands of particles and applying transition model to them, applying noise to them, making measurements for each and every one of them, see which one is more likely, calculating the likelihood, and then resampling, each one of them are very highly demanding in computation. The other thing is they do not perform well when the problem has high dimension. So in this case, the search was only done in 2D, so it's not really that bad. But once you go over higher dimensions, then you cannot really cover the entire domain with a sufficient number of particles. And remember the term curse of dimensionality. So when you are in a high dimensional space, each group of particles will only go to a corner of that space, and the distance between them can go high. And if you want to keep those distances smaller and cover the entire area or most of the area, you need a very large number of particles, which practically might not be feasible to track. Since you limit the number of particles really, then there are some areas of the space that you cannot physically cover. Okay, and you miss them. Then, as we said, since we only use finitely many particles to approximate the probability distribution, there definitely will be a bias in the posterior estimate. Of course, this is just an approximation. What else? In applications such as robot localization, one of the things we have to be very careful is when the robot does not move between the two steps. Okay, that is very tricky. If my robot does not move, let's say between this one and this one, right? So they stay in the same place and they don't pass, or sorry, in this case, if they don't move, then I should not resample. I should not what? Resample, because I'm losing the weights of the previous step while the robot has not moved to give me a new measurement. There is no new measurement, there is no motion, so resampling should not be done. You see, the resampling is done After what? After I make some transition here. If this part is not done, then I better what? Not resample. So that is very, very what? Critical. And you see here that if x of t is the same as x of t minus 1, you better what? You see here that we should not resample, or about the weights, because resampling is changing the weights basically. You can say that. The weights, you can set them equal to 1 if resampling took place. So give them all smaller equal weight of 1. But if no resampling took place, just go with that update that we had. Okay? And don't give them equal weight. So keep that, some bigger, some smaller. Right? So here, this means keep them all like that. Here means what? Do this. Keep that previous one. Here means no. Basically, give them all weight of 1. So that is very important. Finally, there are two scenarios that we have to talk about. One is, at one extreme, the sensors of the robot are noisy and inaccurate, but your motion model is accurate. In this case, you can still approximate the target distribution, okay, and you can still be efficient. So in particle filters, if your sensors are not so good, but your model for transition is good, you can do a good job. On the other hand, if your model is bad and not accurate, but your sensors are so good, then the distributions that you approximate over time would deviate from the actual one, and you can go inefficient. Okay? And you can see that in the example 2, that if my sensor is perfect, but the model is not, what can happen? Let me show you here. So let's say my model is no good. So although I told it to move forward, but now my basically transition model predicts that instead of these guys passing through those openings, they move maybe what a little bit to the right and forward. So if that's the case, maybe this guy comes here instead. Right? And look at the difference in what it can see. Right now, this guy sees this, which, remember, it was this corner which would match my perfectly accurate sensor, which gives me that perfect corner. On the other hand, this guy would see what? This guy would only see a line, which will give me very, very small likelihood for such measurement. So although this one was the dominant one and it was the accurate one, but guess what? Now, because this motion model is wrong and my robot is estimated to be in the wrong location, my sensor measurements, although being very good, they are being completely wrong. And this two cannot be compared. And so this likelihood here is going to be very bad, this one. So that ruins everything. But, as I said, if my model is good, so I still predict that this robot comes from here to here, but the sensor does not give me something perfect like that. As I said, it gives me something like this. There is still a good chance that this measurement here and this measurement, basically, if you compare them, give you a good likelihood that they are the same, 80% they are the same or something. But this one and this one clearly are not the same at all. So the importance of model is more than the importance of the sensor. Okay, and if your model is bad and sensor is good, guess what? Your algorithm might not do that well. So hopefully you learned something about particle filters or Monte Carlo simulations, which are used very much in robots for localization and in other applications. And I'll see you in the next video. Thank you.